Okay, that looks good. So we're back. Online's just small technical glitch, or not so small. See how it goes further. And so hydrogen, we remove how we modeled hydrogen before. We add a hydrogen bus, and now we add connections between the hydrogen and the electricity bus. One of them being the electrolyzers with efficiency and some capital cost as an extendable component. And on the other side, we're choosing here a fuel cell with another efficiency, just going the way backward from hydrogen to electricity with some example capital cost. And now we have made the connections between the electricity and hydrogen bus, and now we need a component that keeps track of the state of charge of our storage medium at the hydrogen bus. And for that, we use the store component, so not the storage unit component, which assumes a fixed energy to power ratio of a storage unit, but just a more general store unit. We call it hydrogen storage. That connects to the hydrogen bus, hydrogen storage carrier. And here we say the E norm is extendable. It's now E because it's related to the capacity, or the capital cost here is related to the megawatt hours of energy that this component can hold. So the investment variable is not in units of megawatts, but in units of megawatt hours. So how big the storage is. And we also, like we have with previous storage, we impose that this storage should be cyclic across the year that we are modeling, so that we can kind of not have a net transfer of energy inside our year. And what we're going to do, we can also add another demand on the hydrogen bus. And when we add, and the demands that we add are always in the unit of the bus we attach it to. And we could say, for example, we take a PSAT that is just our electricity demand that we have from the previous model. And if you take the average, is about 55 gigawatts. And just for as an example, say we add this as a load, call it hydrogen demand, to the bus hydrogen, to the carrier hydrogen, and set the load to that PSAT value. So that would just add a constant load to the hydrogen bus. And for plotting, it will be useful to add the different carriers for the electrolyzer, the fuel cell, and so on to the carrier as carrier components, just so that we have colors defined later for plotting. And then we can already do a first solve here. And we're going to use HEIS as a solver. And what we will be able to see, we'll be able to continue to use our statistics functions, for example, for the optimal capacity, but we'll now have more components there. We have kind of capacities for the electrolyzers and the fuel cells. And maybe I have to say one word about what these values represent. For links, the capacity is always measured in the unit of bus 0. So the electrolyzer with bus 0 electricity has a capacity of 168 gigawatts electric capacity, and the fuel cell with bus 0 on the hydrogen side it has a 76 gigawatt hydrogen capacity. So it can take in 1 hour 76 gigawatt hours of fuel, and you have to multiply that with the efficiency to get the same the rated capacity in terms of bus 1, in this case the electricity bus. Just something it's just a matter of definition, just something that one has to take care of when looking at these values. And for the store, the unit here would be in the unit of the capacity, of the of the investment variable, and for the store that would be, in this case, because we already divided by 1000, be gigawatt hours and not gigawatts, not a unit of power. So one thing that is now interesting, for example, we can look at the state of charge over the optimization period. You can see here a nice seasonal profile. It's basically emptied twice in a year by just looking at the kind of E, so the energy state of charge of the stores. In this case, we only have one. Previously, we looked at this energy balance when we only had the electricity system, and that you can still do. You maybe just define what bus carriers you want to look at. So this will give you an energy balance of just the electricity side, all the buses that have the carrier electricity, which in our case is just one, and you can see then kind of in what periods you have a lot of wind, when the electrolyzers runs, when the batteries in green run, and so on. But now that we have a different carrier as a bus, we can also look at the same chart from the different angle, like we did last week. We can look at it from the hydrogen side and kind of how the production of hydrogen is aligned with the consumption of hydrogen. Let's zoom in again. You can see here how, not super well legible. I guess you can see two different colors on the top chart. Yes, you see kind of how the electrolyzers runs a bit erratically throughout the months, 2 months in this case. You can see in orange how the fuel cell only operates and only withdraws hydrogen in a few hours, and then the kind of other purple color is just the kind of hydrogen storage that shows up as a consumption if it charges, and then as a positive value when kind of the hydrogen is being used but not produced in the same time. It's just netting out the difference in the energy balance. You can also filter it out, and then you can see kind of, no, that's not a good plot. Anyway, good. All right, so that's what we can do. We can do that for any carrier. So once we add now different carriers, we can do the same energy balance also, for example, for the heat bus, which we're going to add next. Follows the same principle. We would add a heat bus with a carrier heat. I brought one example of a heat load time series, and which we can just add like any other node now to the heat bus with the same parameters. And here, kind of the time index of PSET just aligns with our snapshots. And it's a good idea to just verify that the loads have been added correctly. So if we look at n loads t PSET, so that's where our loads are stored, we have in blue our electricity demand from last week. And now we have the heat demand, the seasonal heat demand on the heat bus. That's really a heat demand. It's not a power demand for heat, because we want the model to decide between electric heat pumps and, for example, a gas boiler or something else. So we've got the bus, we've got the demand on the bus. Now we need to figure out what can supply that heat. And one way to connect to the electricity would be through heat pumps. And last week, or 2 weeks, or yeah, was it actually 2 weeks ago, we looked at this kind of data inputs for how we can calculate this time-varying coefficient of performance, kind of the efficiency from electricity to heat of a heat pump as a function of the ambient air temperature and the storage temperature, the so-called sink temperature. And here I brought a time series for an air-sourced heat pump, or I actually brought kind of ambient temperature time series. It'll look like this. So kind of -1, -2 degrees in 1st of January. And these we take as input for this function here. So this Python function just implements this function that gives you for the delta temperature, and our sink temperature is here just a fixed 55 degrees. It will give you the coefficient of performance. So how many units of electricity you need to produce, how many units of heat you get out of 1 unit of electricity. So this is kind of the time series that come out of that. For example, here we would get 3.5 units of heat out of 1 unit of electricity consumed. You can also see that is kind of, if you plot one against the other, that is this kind of mildly quadratic function. Okay, how do we add that to the model? Again, it's a link from electricity to heat this time. And the COP, we can just deal with it as an efficiency. So we just pass our COP function of the temperature as efficiency. Again, it has the snapshots as an index, so it's time indexed. The component is extendable. We add some capital cost and also the carrier. We can add other heating technologies. Some are a bit simpler. For example, we could just add a plain resistive heater, which doesn't have this time-varying efficiency. Then we could just put 90% as an efficiency, and the capital cost is maybe a little bit or substantially cheaper. And then the model can weigh between the extra cost of the heat pump versus the higher efficiency of the heat pump on the heat side. To add that, we can also add the different carriers again, or plotting later. And then one other thing is that now is the first component that would connect to more than 2 buses, would be a combined heat and power unit. So think of district heating systems, like in Berlin. There's a couple of power plants that produce power, but also heat for the district heating. We're going to model that with gas. So first thing we need to do temporarily, we'll remove the CO2 limit, which is set to 0. And now we add another bus. We add a gas bus, and the CHP unit power plant would connect from gas to both electricity and heat. So it has 2 outputs, and that we'll get to in a moment. But maybe let's focus on the gas side first. So what we want to do is here we want to allow the system to use up to 100 terawatt hours of gas with a fuel cost of 150 euros per megawatt hour. In this case, we can add to the gas bus, which is kind of our resource bus or fuel bus. We can add a gas storage. And this time, this storage is not cyclic. We use the feature that it can be depleted over the optimization horizon. We say it has an initial filling level of 100 terawatt hours with the same capacity. And for a marginal cost of 150 euros, it can use energy from that store. It doesn't have to use it, but if it thinks it's useful to buy the gas for 150 euros per megawatt hour, then it can use up to 100 terawatt hours of that. So that is our supply of the gas. And when we do that, we also need to change a little bit how we modeled the gas power plant that doesn't produce heat. So previously, in 2 weeks ago, we had an OCGT power plant, which we just added as a generator. And we didn't think about we just added the fuel costs to the marginal cost of that generator. But now we actually have a gas bus. And now we have to model the kind of gas power plant a little bit differently, in that rather than the generator putting electricity into the model at the cost, at some marginal cost that includes the gas cost, we actually have the gas carrier resolved explicitly. So that means that we also should model an open cycle gas turbine as a link and not as a generator, a link that connects two buses with one another. So you'd add now a link that connects gas to electricity with a carrier OCGT, some capital cost, some efficiency, and that's it, basically. And now we're at this point where we have this component, combined heat and power unit, that produces two outputs. And for that, you can use basically the same parameters. So previously we had bus 0 and bus 1. Now we can also add a bus 2, which is just another output. And correspondingly, we would add an efficiency 2. So the efficiency 2 would tell you the efficiency from gas to heat. So how many units of heat you get out of a unit of gas that is consumed, just like efficiency, and it's not called efficiency 1, would tell you the amount of electricity per unit of gas. So in that sense, what you have to remember is that bus 0 is always the input, and then any bus 1 to n would be an output. There are ways to model multiple inputs, single output, in which case you would have negative efficiencies, but that's a bit of a brain knot. So we'll keep it at kind of one input, two outputs for the moment. Okay, and we'll add the carriers for plotting, just adding some colors, and we can do another solve. Any questions so far? No? Good. See? So that was successful. We can look at the total system cost. And again, we can now look at the energy balance, and we can specify the bus carrier, and we get kind of a kind of net energy balance for each of the components that is connected to the heat side from the perspective of the heat buses. And here we see a lot of heat pumps. We see bits of CHP to supply the heat load. And if you sum up this series, you would get 0 exactly, up to rounding errors. And you can look at the same from the perspective of the electricity side, where you would then see kind of how much electricity is consumed for electrolysis, how much for electricity, and how much for the heat pumps, and how it is supplied. And of course, we can also look at the energy balance plot time series for the heat bus. Okay. So one interesting thing that we can also add now, we can also add different storage technologies at the different buses. For example, a long duration heat storage here, something where we can bridge, where we can store heat over a longer time. And there's one extra parameter that we didn't talk about yet, is kind of the standing loss. And the standing loss would just tell you about the decay of energy stored in storage over time without actually using it. So this is set up so I think that kind of after half a year, the SOC reduces to half if it was completely full at the kind of beginning of the half year. We can add this component and solve this again, and it can potentially kind of, if it is attractive to the model to build this technology, the cost that we should see at the end should be slightly cheaper. So what you also notice with these sector-coupled models, the more components you add, and especially those that can kind of trade off long duration energy storage over longer time periods, they will also take a little bit longer to solve. So I think we get here now 128. Previously we had 141, I think. So the costs here are reduced. And now in our energy balance, we see that there's some amount of energy lost in the heat storage. And let's see if we can also see that in the balance plot. We can just disable all the other technologies, and we can then see how the there's a tendency for the storage to discharge over the winter month and then charge over the summer. Okay, and yeah, filling levels of the storage. You can also see, in addition to the hydrogen storage in blue, the heat storage in red. Good. Okay, so the third and last segment of this notebook is probably a little bit more intricate. And I mean, with everything that I'm showing, it's kind of very stylized modeling, but for modeling electric vehicles, where you have some amount of demand side management and maybe also some, you could assume that you have some vehicle to grid technology there to discharge the battery from the electric vehicle into the grid. We can also model that with a separate bus that represents our fleet of EVs, not necessarily a single EV. And what we need now is kind of some profile of the electric vehicle consumption. And that's that's already a profile here in gigawatts that we just assume with a certain size of the fleet and certain mobility patterns. But let's just assume that is kind of the power that is actually consumed by the vehicle when it's driving. And we can add this to the EV bus as a load. And the problem that we have now is we can only connect the electricity bus with the EV bus for the fraction of electric vehicles that we assume that are plugged in. So we need to impose on the link that we have from electricity to the electric vehicle, we need to impose some capacity limits that are time varying, that are following this availability profile. So if you assume the electric vehicles, they have a fixed charging power rating, and only 65% are connected, then the total charging power of all the electric vehicles times 65% would be the maximum that you can charge in the grid at the time, because the rest of the fleet is just not connected to the grid. So what we can do is that we, first of all, calculate the kind of total power by multiplying number of cars with our assumed charging rate here of 11 kilowatts. That gives us a p-norm value for our link. And the link basically looks just like the electrolysis, for example, that turns electricity to heat. Here we have electricity to EVs with set fixed capacity. So that's not a component that we assume is extendable. We just assume the number of electric vehicles is given. And here we add, just like we add, for example, for the wind and solar generators, a P max per unit as availability profile that kind of downrates our capacity in the different time steps. And we can also consider an efficiency here. And in principle, we can also do the other way around with a vehicle to grid link, same availability constraints. We could also assume that maybe only 50% of the electric vehicles participate in the demand side management, that we could also do and downscale the capacity further. do that. And then now the trick is, well, how do we align the time series of the consumption of the electric vehicles that's just following the mobility pattern with the charging periods? Well, and that's the demand side management essentially. Well, we would model that as a storage. We would model that as a storage, as basically as the battery of the electric vehicles, where we would say, well, the total energy of all the batteries is just kind of the number of cars times the energy per electric vehicle, and then some fraction of cars that participate in smart charging, and a potentially a demand side management profile where we could impose some constraints. For example, we would maybe say, well, at each morning at 6 or 7 or 8, we require that state of charge is at least 75%. And that we can impose on a store component that represents the EV battery with set energy capacity and a E-min per unit, so a minimum per unit charging level. That is just our demand side management profile with these kind of constraints for individual snapshots. Add some carriers and solve that, and then we can look at what the costs look like. And that is, of course, now going to be more expensive because we added more loads to that. And it's also going to take slightly longer to solve.
Maybe one small side question.
Yes.
I was thinking about how you could do this in an highly resolved network. When you have like these 3 different layers of bus type, but then maybe hundreds or tens of technical buses, with different routes or different kinds of things or space of links between them.
Yeah.
How do you build it in that way?
Yes, so in principle, it looks very similar. You just you're just basically duplicating this for the number of regions that you are representing. So, I mean, all this basically we did for one node, and we would have this, if we have 100 or 200 nodes, we would have exactly the same structural setup, just with different time series for the different regions, of course. But the code looks still very similar, only that we would maybe have something like an pandas index of kind of our buses, like different, let's say we have country resolution or something like that. And then we would add, let's call that S, and then we have set up a bit like the buses would be called region plus some suffix, maybe electricity. We could do, it would look mostly a bit like this. So all the components that are named after the region, they have some identifier of the region. The carriers all stay the same so that you can aggregate them later. And what we have as an additional parameter often is the location, so that if we want to filter, basically just cut out one or a subset of the regions, then we can filter by that attribute. But then the enorm here, which is currently a scalar, would be a pandas series, so it has just one dimension more, and the DSM profile would be a pandas data frame, also has just one dimension more, that would be kind of indexed like this. So structurally it's super similar, it's just that you have to work with an additional dimension there.
certain kind of electrolyzer power at one link, to say it would be like an innovation of data frame.
Yeah, exactly. Yeah, exactly. Yeah. Right. Yeah, so let's wrap that up. Now we have an energy balance on the electricity side, which has additional consumers here. The EV chargers, 227 kilowatts. We have 132 billion euros per year as costs. And now we can look at the kind of time series again. I guess that's a little bit less interesting when you have seen all the other balances already before. But you can now see how kind of on the demand side, we have kind of the gray bits that are just our regular electricity demand, purple, the hydrogen, and then in green, the electric vehicles. And that is all kind of the balancing here for every hour. That is all just managed by the model. Yeah, so I think kind of that's as far as the PyPSA modeling goes in this course. There's of course a lot more that you can do, and there's a lot more you could in principle explore. So if your hunger is not satisfied yet, you can always go to docs.pypsa.org, where there's an extensive list of kind of examples. So there's a couple of features that we haven't talked about at all. For example, pathway planning, so where it's also a decision of the model when certain capacities are built. Right now, we only look at kind of, we have a target for CO2 emission reduction and look at kind of if we can decide on the perfect system and the perfect mix, what should it be? In the pathway planning, the model gets a budget from, say, now to 2050, and the model can then allocate capacity expansion in different planning horizons in 2030. Should it be built in 2030, 2040, or 2050? There's some bits on stochastic optimization, for example, where you don't know all the things, all the parameters that go into the model. You don't know what the gas price will be. You don't know what a CO2 price will be. And you can formulate optimization models that take into account this optimization, this uncertainty, and try to optimize for the kind of expected value. Or, and I think I mentioned that in one of the lectures, this modeling to generate alternatives to look for near optimal designs that are kind of only marginally more expensive than the cost optimal solution, but maybe, can get rid of some of the kind of not publicly accepted technologies. Other things I would say are interesting, maybe, for example, unit commitment we didn't talk about. So some of the conventional power plants, they have constraints on how quickly they can change their output. So these would be additional constraints that could be added to the model, and a couple more, but that really is up to your taste, what you find interesting. So if you want to explore more, then you're more than welcome to go through the examples, and I'm also there to answer questions.